Hello all, welcome to the tutorial 2 of Phononic Crystal simulation using COMSOL. So in the last tutorial we learned how to evaluate the band structure of a phononic crystal using its unit cell and using following the steps prescribed in this document using COMSOL Multiphysics. So in this video we learn how to calculate a transmission spectrum of a phononic crystal using COMSOL, and the steps are already described in this document. So if you try these steps, you easily able to evaluate transmission spectrum. So transmission spectrum is nothing but a plot of transmission ratio of the phononic crystal versus its uh, I would say frequency. So frequency versus the transmission loss plot is called transmission spectrum, and transmission loss is defined as 20 times log d out by d in. So d out is the displacement at the output probe and d in is the displacement at the input probe. So it basically calculates how much displacement is observed from the input with respect displacement observed at the output with respect to the input. So the model will be something like this. This is a finite phononic crystal model. So here let's say this is the input probe and here it's an output probe. So uh, when we apply displacement in the input probe, it essentially means we are exciting elastic waves at the input probe, and we collect the displacement at the output probe. Essentially, we are collecting the elastic wave at the output probe, elastic wave magnitude. So when we take the ratio, it will show how much it has transmitted from the input. So it is a kind of it's a kind of analysis for a finite phononic crystal, because in the band structure we work with unit cell and we apply periodic conditions. It means it's the infinitely periodic phononic crystal. But in real world we won't work with infinite structures, we work with the finite structures. So that means we need to evaluate something, uh, something meaningful analysis just for the finite structures. So this transmission loss has been a good way to work out the correlation between band gap and the same band gap property for finite uh, structures. So if we so the transmission spectrum looks something like this. So we can see the lower transmission in the band gap region, which is observed in the band structure. So it's a kind of a verification for the band structure plot. And so I'll show you the model which is used to calculate this transmission spectrum. So basically, in the first tutorial, we use this model to calculate the band structure. Now we'll use this model to calculate the transmission spectrum. So this phononic crystal is uh, 4 cross 5 in in x and y directions, and it has like 4 cross 5 unit cells. So as you can see, the geometry just has a block, but it is now 6 times, including this extra PML block. So what's PML we'll see later. And the cylinders, first the cylinder is created at this space, and then we can create an array using something using this transforms tab in the geometry section. So you can create an array. You can just select and you can give how many unit cells you want in directions and what's the displacement between the unit cells. So displacement between unit cells will be nothing but the lattice constant. And after forming these arrays, you can do the same difference. So you can select this as objects to add, and you can select these cylinders as objects to subtract. So when you build all, finally you will get geometry something like this. So next thing is to, so during this block, we can select a layer on left and right positions. We can give thickness something like a one lattice constant. So this is like this, and this block and this block is especially for PML. So PML selection you can do in the definitions. So in the definitions, go to uh, perfectly matched layer, and when you select perfectly matched layer, it automatically asks you to select the regions which you want as a PML. So PML is nothing but it's a kind of interface which changes the coordinate system just for the elastic wave calculations. So it is added to prohibit or remove the unwanted reflections which are collected at the boundary. So at the boundaries, since we are giving excitation of elastic waves using the displacement, so there might be unwanted reflections that are calculated in the transmission spectrum. So to avoid those, we can use PMLs, perfectly matched layers. So just use a perfectly matched layer and uh, remain other settings as it is. And coming to the, so next thing is to choose material. So we can choose AL material as in the same the band structure calculation. And coming next section is solid mechanics. So in this solid mechanics, we have to provide displacement at input and output probes so that we can capture during calculations, frequency domain calculations, and then we can calculate the transmission spectrum. So in this solid mechanics, to give the displacement, you go here and select prescribed displacement. So the we select prescribed displacement, and you will get here. So if you see, our displacement is uh, it is along this line. So let me show you this view. So the displacement is along this part, the interface between the PML and this phononic crystal. Since it's 3D, we have to give in this way. But if you are using 2D, you can just give an line displacement. So here we will give a surface displacement. That is, so you can give as a prescribed displacement. You can give as 1 mm in the x direction. So mainly we are calculating here the longitudinal waves of the whole elastic wave family, so that the displacement can be given in x direction. So depending upon the type of wave we need, for example, if we need surface waves, generally Rayleigh waves, we give displacement in z direction. And also if we want to calculate low waves or shear horizontal waves, we can give displacement in y direction. So that depends upon the type of waves we are calculating. For now, let's calculate longitudinal waves. So we give displacement in the x direction. 1 mm we can choose as a general value. Anyway, it's the ratio of output by input, so it does not matter in the transmission loss calculation. And yeah, so before going to the mesh, now we have to choose boundary probes to select to calculate the displacement. So in definitions, you can go to probes, and that there are several kind of probes. For now, we can select boundary probe. If you are working with 2D model, you can select edge probe. So here I selected boundary probes, and these boundary probes are at input and output. So I have 1, 2, 3, 4 for input and 1, 2, 3, 4 for output. So let's see the input probe. So similar to the displacement, the surface where we are giving displacement is the surface where we are placing our input probe. So this is the input probe selection, the interface between PML and our phononic crystal. So here you can choose to calculate the expression. So we want to calculate solid dot displacement, and you can give integration methods, whatever. So you can select average, maximum, integral, depending on the analysis. And so the next three probes, which name UI, VI, and WI, these separately calculate U2, V2, and W2, which means the X, Y, and Z components of the displacement at this probe. And similarly, coming to the output probe, it is defined exactly at the other interface of PML and phononic crystal. So here also same, we have four probes. One probe will calculate the displacement. This is basically the average displacement, and to especially if we want to get separate components, we can choose another probes and just evaluate that expression U2, V2, and W2, which means displacement in X, Y, Z directions respectively. So after choosing probes and this probe selections and this model building, you can jump to meshing. So meshing here in the same, I have chosen normal. So depending upon the analysis or required application, we can choose different values, as I said, in band structure calculation. So I choose normal, and let's see, build all. So it builds quite nicely. The meshing is quite nice. So COMSOL automatic uh, does the job automatically. But if the structure is too complex and it has multiple, let's say, modules or multiple kind of device parts, then we can choose different mesh for different parts or different blocks of same design component. Yeah. So since after this meshing and all, the next part is to calculate the transmission spectrum. So for that, you can choose frequency domain study. So to add the study, you can go here, study tab, and click add study. So it will show whatever studies you want to add. So you can click frequency domain and add it. Just click and add study. It will add. So for now, I already added the study, so I'm deleting this. So the study 4, in which we calculate the transmission spectrum. So in the frequency domain, it asks which frequency unit. Since we are calculating in kilohertz, I just placed kilohertz, and you need to specify a range of frequencies which have some particular step size, so that it can calculate each and every point of the frequency range. So here I have chosen from 30 to 100, step size of 0.05, all in kilohertz. Or you can use some particular frequency values. It gives us calculates in the same range, whatever you choose. And here physics and variable selection, since our component 4 is uses solid mechanics 2 study. Here you can see solid 2. So we select solid 2, and in the mesh selection you can choose mesh 4 for this component 4 here, and for geometry 1 we can select no mesh, because anyway we are not calculating results for the unit cell. So after this, you can just, so in this results while solving, you can choose whatever probes you want. So you can choose all probes, and it will calculate the transmission loss. So let us go ahead and compute this. Let me see. So it took 3 hours for me because uh, it's normal mesh, and we have finite cell ranging from, let me see the, so from 0 to 200 I guess. So it might take time depending upon the range also. So here if we give just steps, let's say 1 kilohertz, it will go fast, but since I given 0.05 kilohertz, so it took 3 hours for me. And the thing is, the smaller your step size is, so the neat, or the you know curve graph you will get in transmission loss spectrum. So after that, you can actually, once you complete the analysis, that study, this computing the study, you'll get something, a probe plot. So here it will show what are the displacements recorded at the probes which you have designed, which you have defined earlier. And so it's similar, you can create a new plot, 1D plot group, name it as transmission loss, and give x and y labels as frequency and transmission spectrum. And let's say you can choose here limits, max and min limits, and you add a global plot, and then go to global. So in the global, select the study for which we have studied, which we have did for frequency domain. And so in parameter selection, select all, since we need all frequency range. And so as we know, the formula for transmission loss is 20 log 10 output by input. So you can reference the output probe, since the output probe name is DO and input probe name is DI. So and it's under component 4, comp4. So you can just select comp4.do by comp4.di, which calculates the ratio of output by input displacements, and add this 20 log 10 expression, so that we can directly calculate transmission loss in dB value. So here you can choose settings, x-axis parameter, and unit kilohertz. So once you plot it, you might see a figure something like this. And let's say we want to study from 35 to 70, so you can uh, reduce your x space. Also you can limit the upper x-axis to, let's say, 1. So this is a kind of transmission loss spectrum for this phononic crystal. So as you can see, there is a gap between some around 55 to let's say 62.6. So which is in our band structure plot. So if we go to the band structure plot, so we see band gap from 56.5 to 62.5. That is what we observe, sorry, we observe in this transmission loss. And these might be I would say other gaps. For example, if you see, so actually, since we are giving displacement in x direction, so it is like calculating at the x point in the calculating transmission loss in gamma x direction, reciprocal lattice, so that if you see there is some kind of partial gap just between these two bands. in this gamma x direction. So that is what we can observe this band is here from 45 to somewhere around 45 to 60. So that those are these partial gaps which you can observe, but the actual complete band gap is from 56 to 62. That is what is observed from here to here. So in this document I have marked this band gap, which is the actual complete band gap. Though this might be some partial band gap. So this is the actual band gap. Control it to 70. So this is the actual band gap from here to here. This might be some partial band gap just in gamma x direction. Yeah, so uh, this is how you calculate transmission loss of a phononic crystal plate. It's a simple structure which I have taken in this demo, but